Um, we are moving into the application portion of our derivatives. So today we're going to talk about related rates, and all we're really using are implicit differentiation, which we could have covered when we did implicit differentiation, but I pulled it out. We're going to cover it today. And then we move into curve sketching for our functions. And so there's a little bit of a change on the calendar. I don't know that y'all really care. But the quiz, there was a quiz. I planned on having a quiz on Thursday. The quiz over this week's material will instead be on Monday next week. Okay, just so you know, there'll be a quiz over this week's material Monday of next week. Okay, so what we're going to talk about is these related rates. And it's basically, like I said, it's just applications of functions using derivatives. So I did post the notes, didn't I? Sure. Positive? Brennan? No notes posted, huh? No notes posted.
There was a Pearson activity.
Pearson activity?
Related rates.
Mhm.
Be on the 14th. That's all. Yeah, exactly. But I'm saying that's all I saw.
Huh. All right. Well, I apologize for not posting it because I had them. All right, so we'll look at it this way. Our related rates are ideas that basically compute the rate of change of one quantity or another. That's kind of what we're looking at. Remember that when we take the derivative of something, it is taking the derivative of some value with respect to time in essence. Okay, so that's kind of what we just want to keep in mind. So that's the related rates that we're focusing on here. So we do it using implicit differentiation and the chain rule and so forth, but an example of that looks something like this. So we want to know when water is draining out of a conical tank, the volume, the radius, and the height of the water level are all functions of time. Okay. And we want to then take the derivative to be able to figure out what an unknown rate is, like what quantity or what is the rate of change of some unknown rate. Most of what we need to know is going to take some known formula, okay? And so we'll try to work on those formulas. I don't know if you all remember the volume formula for a cone. So most solid figures, when you're talking about the volume of them though, for a cylinder, let's say, okay, think about a cylinder. It would be the area of a circle, and then you're just going to stack that circle on top of each other to fill itself up to the height, right? So when you're thinking of volume of known figures, try to think about how could I break it down into the area times a height. Cones, pyramids, those are all 1/3 of that volume that you would normally know. So the volume of a cone is 1/3 the volume of a cylinder. All right. So just kind of a reminder on some of those. Now, you don't need to write these things down. I just want to point a few of them out to you. Okay. When we go about solving our related rates, all right, we're going to try to write down all of the given quantities that we have. That's kind of a natural thing to do. Okay. And then if a sketch is not given, we're going to try to make a rough sketch. Okay. We want to also write down our equation that's going to relate our variables together. Okay. Seems rather simple. Then we take the derivative with respect to time on both sides and plug in all of our givens at the end. All right, so it's kind of a 4-step process. We'll see how we work in just a minute. Okay, and just some other information that we kind of are looking at here. You know, if the velocity of a car after traveling for 1 hour is 50 miles per hour. Obviously, that would be dx dt, so 50 miles per hour, right? So you're always looking for the rate in the statements. And those are just a couple of examples of it. A gear is revolving at a rate of 25 revolutions per minute. So that's angular speed, right? That's going to come back and we're going to look at that a little bit again. So that would be the 25 times 2 pi. At 2 pi with 1 revolution, right? So 25 times 2 pi radians per minute makes it into d theta dt. Okay, and we'll look at one of those in a minute. Okay, so let's just kind of get started here. So we have air is being pumped into a spherical balloon, and it's being pumped in at a rate of 4.5 cubic feet per minute. We want to find the rate of change of the radius with the rate. We want to find the rate of change of the radius when the radius is 2 feet. All right, all you drafting people in here, don't make fun of my drawing when I draw this sphere. I'm going to draw it, maybe it looks something like this. Does that look good? Sphere? Now we believe it's a sphere? Yeah? Okay. So air is being pumped into a spherical balloon at a rate of 45 cubic feet. 4.5 cubic feet. So right here, we're given a rate automatically. And cubic feet implies, just looking at the units there, cubic feet implies volume, right? Centimeters cubed, or feet cubed, I should say. So dV dt is given to us at 4.5 cubic feet per minute. I know that, so this is what I know. I know dV dt. I know that the volume, and I'm going to tell you this, that volume for a sphere is 4/3 pi r cubed. Even though I told it to you, we really do know that. You would want to go out and find that formula if you didn't know it already. Now, what I want to find, I would like to find the rate of change for the radius. So dr dt when r is equal to 2 feet. So that's what I know. So we're going to take our formula right here. And when I'm looking at the formula, I have volume, which is V. I have R, which is given to me, and dV dt, dr dt. So I have pretty much everything I need to be able to move forth. So the second thing I want to do is I now want to take the derivative of both sides with respect to t. And the derivative of v with respect to dt would just be dv dt, right? The v disappears implicitly. Okay. And then I've got 4/3 or 4 pi over 3 that I'm going to pull out or pull out in front. And then we have r cubed, which becomes r squared, or excuse me, 3r squared. 3r squared when I take the derivative of r, dr dt. Okay, didn't do anything we haven't done before. Before I go too much further, let me just kind of clean this up a little bit. dV dt would be equal to 4 pi r squared dr dt. Did I miss anything there? No? Okay, so here, I want to know what dr dt is. So I'm going to solve for it. I typically don't go much further than this because if you look as far as solving and isolating, if you look at it, I'm fixing to replace dv dt because I know what that is. That was given to me in the problem. I'm going to replace r squared because that was given to me in the problem. So I'm not really going to spend a whole lot of my energy rearranging this algebraically. I'm going to start plugging some numbers in because I'm going to solve for dr dt. Okay. So dv dt is 4.5. That's equal to 4 pi times 2 squared dr dt. Okay, so I would end up with 4.5 would be equal to 16 pi dr dt. And then I'm going to divide both sides by 16 pi. And I'm going to get a decimal value. What kind of decimal value do y'all get when you divide both sides by 16 pi? Let's go to 3 decimal places. Yes, sir.
0.090.
0.090?
Yes, because it's 0.0895.
0.090 feet per minute. The radius is changing at a rate of 0.09 feet per minute when the radius is 2 feet. Okay, so at that instant that the radius is 2 feet and we have a volume, right? Then we can say that the radius is changing as well, and that's the rate. Okay, so we're just going to use implicit differentiation. I say just use implicit differentiation, all right, and then plug numbers in to simplify from there. Okay. Okay. Questions on that so far? Okay. Let's look at this one. A water tank has the shape of an inverted circular cone like you saw above with a base diameter of 4 meters and a height of 8 meters. If water is being pumped into the tank at a rate of 3 cubic meters per minute, how fast is the height of the water changing when the water is 2 meters deep? That's what we're looking at. So now we're going to draw our inverted circular cone. Okay, we have a base diameter of 4 meters. We have a height of 8 meters. So there's our figure. What do we know? Water's being pumped into the tank at a rate of 3 meters cubed per minute. What is that? dV dt? That's 3 cubic meters per minute. Okay. What do we want to find?
The rate of change in the water is
So the rate of change for, okay, so dH dt. When the height is 2 meters.
Is that derivative?
The dH dt. So whenever it says, I want to know what the rate of change is for something, that's the derivative, okay? And it says how fast is the height of the water changing. So I want to know what the derivative of height is. Okay? And it tells me I want to know that at 2 meters, when it's 2 meters deep. So I'm needing those kind of two things together. Okay, all right. We know the derivative of the volume. So we saw above that volume, the formula for volume is 1/3 or pi over 3. Actually, it's 4/3. No, it's not, excuse me. 1/3 r squared h. That's the volume for a cone. So when we're looking at this, we kind of have a problem because I know dV dt. I know h, I'm going to end up with dH dt, but I have an extra variable in here, r, that's not going to go away when I take the derivative, is it? Because when I take the derivative of r, I get r squared, or 2r dr dt, right? I don't have an r and I don't have a dr dt anywhere in the givens. So what we want to do is we want to rewrite, and we want to take what we have over here and want to be able to write this formula. Okay, so we're going to try to rewrite in terms of V and H. In other words, we want to eliminate R. We want to rewrite R in terms of H. We can do that using proportions. Another way to think of that would be similar triangles, okay, of what we have known over here. All right. And if we look at our figure, I know that we have, when I have a certain height here, call it H, then this is a certain radius, isn't it? Okay. And it would actually be 2 times the radius because it would be a certain diameter, I should say, right? Okay. So if I use known proportions, if I use proportions here, I could say then that however you wanted to set this up, I could use diameter over height is equal to diameter over height. And I have a proportion, don't I? Okay, so I want to solve that proportion. I want to rewrite that for R. So I'm going to end up with 16R is equal to 4H, or R is equal to 4/16 H, or 1/4 H. Everybody understand? I just use similar triangles, or in other words, I use similar proportions, right? Okay. So now I'm going to come back over here and I'm going to take this equation for volume and I'm going to rewrite it, which I would have pi over 3 times 1/4 H squared times H, because I'm replacing R with 1/4 H. And now I'm going to simplify it. So volume would be equal to, what would that be? Pi over 3 times 16 H cubed, and 3 times 16 would be 48, correct? Yes. Okay. So that's the formula for volume written solely in terms of V and H. Now I want to take the derivative with respect to time. So on the left, I get dV dt. On the right, I get pi over 48 times 3H squared dH dt, or dV dt is equal to, that would be pi over 16 h squared dh dt. And now I can just plug everything in that I already know. So dv dt was 3. That's equal to pi over 16 times 2 meters squared dh dt. And so I would just have, what, 3 is equal to pi over 4 dh dt. Divide both sides by pi over 4. And I get 12 over pi, which is the same thing as, what's that to 3 decimal places?
3.820.
Meters per minute. All right. Okay. Now, let's look at this one. An airplane is flying in a flight path that will take it directly over a radar tracking station. So you have your figure here. The distance is decreasing at a rate of 400 miles per hour. So this distance here is decreasing at a rate of 400 miles per hour. So we're getting closer in that direction. When s is equal to 10. So what is the speed of the plane? That's what we are looking for. All right, so draw your triangle on your paper. What do we know? What do we know from that up there? That the distance is decreasing at a rate of 400 miles per hour, right? Okay, so that would be ds dt. 400 miles per hour. When s is equal to 10. All right, and I don't have a whole lot of other stuff in there, do I? All I know is that s is 10. I know that the vertical height is 6 meters. That's about all I know. What kind of formula would I create here? I'm wanting to end up knowing how fast it is, in other words, how fast x is changing here, all right? As the plane is moving in this direction here, right? This length has to be decreasing, the hypotenuse has to be decreasing, right? As the plane is getting closer and closer to this point right above the radar, the hypotenuse has to be getting shorter and shorter, doesn't it? Okay, so the hypotenuse is changing. This distance is changing, so I want to find, first I really kind of need to find dx dt. Which would tell me what is the rate at which this distance is changing, right? Okay. Now, if I'm looking for this horizontal change up here, think about it, what kind of formula would I be using here? What kind of shape do I have?
The triangle.
In a triangle, what kind of formula using a triangle relates all its sides together? Pythagorean theorem, right? Okay. All right, so I do need to know a little bit of information, but I know that I would have this side, 6 squared plus x squared is equal to s squared. Just before I've done anything. Now, why is 6 going to be constant in this particular case?
Because the plane is always 6 miles above.
Very good. So that one is going to be constant. The hypotenuse S is changing. The X distance is changing. So I can kind of simplify it a little further using this. Now, let's take the derivative with respect to both sides, with respect to t for both sides. So the derivative of a constant, that's just going to disappear. But the derivative of x squared becomes 2x dx dt. And that would be equal to the hypotenuse, which would again be 2s ds dt. We are looking for dx dt, and we know everything on the right-hand side, right? We know what ds dt is when s is equal to 10. So I'm missing some information about x, right? Okay, well, what I can do is I can come back and say, okay, well, what is x when s is 10? What is x when s is 10? I can do that by finding, so I'm going to come over here and I'm going to say, okay, well, hold on just a second. I know that this triangle, right, would be 6 squared plus x squared is equal to 10 squared. When s is 10, the vertical height is still 6. I want to know what is x, right? Okay, so I would just take Pythagorean's theorem, find out that this was going to be the square root of 10 squared minus 6 squared, or in other words, 64, which is 8. So what that tells me then is when s is 10, x is 8, and the vertical height never changed, right? And that's what we're going to use to plug in for that missing piece here. So I can come back in and I can say, okay, 2 times 8 dx dt is equal to 2 times 10 times 400, because that was ds dt. Dx dt becomes what? When I divide that off?
500.
500. Now, I forgot this and I keep forgetting it. So I'm going to tell you that I keep forgetting this so you won't forget this. All right? The key to this, there is one part that is important here. And I seem to just always ignore it because I'm only looking for numbers. So I'll tell you that right now. I know that this is decreasing, right? Okay. So in other words, the 400 we should have used should have been a negative 400, because we know that that is decreasing, right? That tells me then that the velocity is negative 500 miles per hour, which is just a position vector, right? So it's moving towards it, right? Or it's moving in whatever the direction, because the opposite would have been positive, right? So negative velocity just means it's moving in that direction. The speed, however, of the plane is the absolute value of velocity. So it would be the positive 500. So whenever you're given that, write it down, that if it's a decreasing rate, you need to make sure that you write it down, because it's on your problems, okay? And I find that I forget it sometimes when I'm not paying attention. Okay, so what did we have to do in this one? You had to identify a formula that was going to relate your information to each other. In this particular case, it was just a Pythagorean theorem, nothing strange about that. But we don't always have all the information for all of those sides. So in order to find out that missing piece, right, we basically solved the triangle at a given point in time. So we knew when S was T, what was X going to be? Okay, that's how come we figured that one out, because we needed to know that information. All right, let's look at this one then. Find the rate of change in the angle of elevation of the camera 10 seconds after liftoff. And what we're going to try to look at here is what's the information that's given to us in that figure. So a television camera at ground level is filming the liftoff of a rocket that is rising vertically according to the position equation. S is equal to 50 t squared. So this side over here has got to be 50 t squared. The camera is 2,000 feet from the launch pad. So I know what S is. I know this information you see here. What do I want to find? Exactly, I'm finding d theta dt. When t is equal to 10 seconds. All right, the only equation that I have here and I'm trying to see where what else we need to look in here. All right, so the only thing I have is if I'm trying to find the rate of change here, right? So I'm trying to find the angle at which this is changing that is related by taking the tangent, right? Because we have our base and we have our height, right? So that is the formula that we're looking at. Tangent of theta is equal to S over 2,000. So let's dive in. Let's take the derivative. The derivative of tangent is secant squared. That would be equal to 1 over 2,000 times ds dt. So we don't know we have a lot of unknowns in here now, don't we? So let's take ds dt. So I could find ds dt by taking the derivative of what we know right there. So the derivative of s equals 50t squared would look like what? Y'all tell me. Okay, so ds dt is equal to 100t, because I'm taking that with respect to time in the first place. Now, secant squared over here. I did not take the derivative of this side fully, did we? It should be secant squared theta d theta dt. So d theta dt would be 1 over 2000 times, let's substitute in for ds dt. That's going to be 100t and 1 over secant squared theta if I move secant squared theta to the right. D theta dt would be 100t over 2000. Can I rewrite 1 over secant squared using an identity? What would it be? Cosine squared? Okay. So we know what t is. I need to figure out what cosine squared theta is. So how do I find cosine squared theta using the figure that I have over here? How do I find cosine of theta? What's cosine of theta defined as? Adjacent over hypotenuse? That's right. So what do we think the hypotenuse then would be here? Wouldn't the hypotenuse, say that again?
Hypotenuse is the.
Oh, wait.
No, the hypotenuse is not s over 2000. That's what tangent is. Okay, so let's think about this down here. If I have a triangle who has a side of 2000 and another side of 50t, how can I rewrite this hypotenuse in terms of the sides? Wouldn't that be the square root of 2000 squared plus 50t squared? Is that the side? Hypotenuse, it's just Pythagorean's theorem, right? Square root of one side squared plus the other side squared. So just like Sam said, if that's theta, then
Wait, is it 52 or 52 squared? Above
it's 50t squared, yeah. So cosine of theta has got to be 2000 over that hypotenuse. 2000 squared plus 50t squared squared. So now I can come back to my formula and I can say, okay, d theta dt is equal to the t over 100 t over 2000 times cosine theta, which is 2000 over square root of 2000 squared plus 50t squared. Everything in there is now written in terms of just t, isn't it? And I know what t is. T is 10. We were told at the beginning that t is 10. Yes, ma'am?
When we square that whole.
Yes, thank you. Thanks for the catch. Because of that square right there. Very good. So now we can just plug in our t. So plug in t and tell me what you get.
T is just 10 or T is
It's
10
10
seconds?
10 seconds. You get 2 over 29, which would be what? 0369. You all get 0.069 radians per second.
Yeah. Are we gonna need to provide it? Are
2 over 29,
we gonna have to provide it?
unless, it depends on if they ask you to give it as a reduced fraction. So sometimes, even though you have known information, you have to kind of go back and see, what am I missing? How can I fill in some of these extra blanks? Okay? Okay, the last problem that we have on here. Doesn't that look familiar? This is the same picture even. We already know how this thing works, don't we? So it says, in the engine shown below, a 7-inch connecting rod is fastened to a crank of radius 3 inches. The crankshaft rotates counterclockwise at a constant rate of 200, it should say, revolutions per minute. Find the velocity of the piston when theta is pi over 3. So we are, what do we know? we know that our revolutions per minute right here, which was d theta dt, is equal to 200 revolutions times 2 pi for each individual revolution, right? Which turns it into radians per minute, revolutions per minute. Yep, so when I converted the revolutions into radians by multiplying by 2 pi, I end up with a unit of radians per minute. So we have 400 pi radians per minute. And we want to find the velocity of the piston, which is how fast this is changing, right? Because this is moving. Find dx dt when theta is equal to pi over 3. So what kind of formula am I going to use to relate all that together? It's not a right triangle. So what's the only other formula I can use?
Some difference.
Law of cosines? Law of cosines. I have to use law of cosines here, okay? Okay, so for our law of cosines, so for our formula that we're looking at, we have, and I want to, I think I just chose to write it as 7 squared is equal to, because it's across from the angle, so 7 squared is equal to 3 squared plus x squared minus 2 times those sides, 3 times x, times the cosine of theta. And I chose that because cosine theta, or theta is here, and so I have to, the formula is written so that it's the side across from the angle. So let's simplify this. And so 7 squared is 49, and I'm going to subtract 3 squared, which is 9. So I end up with 40 is equal to x squared minus 6x cosine theta. So when I take the derivative of this, I end up with, let's take the derivative of both sides. So what do I get when I take the derivative of the left? 0 is equal to 2x dx dt minus, so this is the first times the derivative of the second minus sine theta d theta dt plus the derivative of the first, which would be dx dt times cosine theta. So I have 0 is equal to 2x times dx dt plus 6x sine theta d theta dt minus 6 cosine theta dx dt. Because I just distribute my -6 into there. So I know what, I'm looking for dx dt. I know what d theta dt is. I know what theta is, but I don't know what x is, do I? So we're back to that same problem of I've got kind of an extra variable in there and I don't know what the value of that variable is. But I can come back and I can say, all right, I need to know what x is. So I want to know, I need to know x when theta is pi over 3. And I'm actually going to use this 40 is equal to x squared minus 6x cosine theta, because that was basically the same thing that we did before using Pythagorean's theorem to find that extra side, right? So it's the same thing, only I'm using the law of cosines here. So I'm going to simplify that and solve. So I have 40 is equal to x squared minus 6x times the cosine of theta, or times the cosine of pi over 3. So 40 is equal to x squared minus 6x. What's the cosine of pi over 3? It's 1/2. 40 is equal to then x squared minus 3x. So it's a quadratic equation, x squared minus 3x minus 40. First term is 1, last term, so what are the factors of 40 that subtract to give me 3? X minus 8, x plus 5. So x has to be equal to a positive 8 or a negative 5. But I can throw out the negative 5 because I'm looking for an actual distance here. So I'm going to come back to our formula that we were working on here. And I'm going to gather up my dx dt's on the left. So I'm going to have a positive 6 cosine theta dx dt minus 2x dx dt is equal to 6x sine theta d theta dt. Factor dx dt out, I'm left with 6 cosine theta minus 2x is equal to the right. And divide everything by what's next to dx dt. And you end up with, on the right-hand side, 6x sine theta d theta dt in the numerator, 6 cosine theta minus 2x in the denominator. And I have x theta and d theta dt. So I'm gonna plug them in. So 6 times 8 times the sine of pi over 3 times 400 radians per minute, or 400 pi, divided by 6 cosine pi over 3 minus 2 times 8. So I want you to simplify this and give me both the exact and the decimal value. Once you multiply all that out, you get 9,600 pi times the square root of 3 all over -13. You get -418.23. Let's try it again. That's the right answer as far as the exact answer. 9,600 pi times the square root of 3 divided by -13. $400 pi, so 400 times 48. Right? Keep simplifying. Okay? All right. So here's a paper, there's 8 problems on it. This is gonna count for a quiz grade. It's due by Thursday. You hand it in to me at the beginning of class on Thursday. So what I want you to do is, you're gonna spend the rest of the class period working on it on a separate sheet of paper, like a clean sheet of paper that you're gonna turn in to me. Have questions you can ask. And I don't mind if you work together as long as you can still produce answers for yourself on a test.